Imagine processing a 1 million token context window, but only using 10% of the KV cache and 27% of the compute. I mean, sounds like an architecture pipe dream. Right?
Yeah, completely impossible on paper.
Right, but today, we're looking at the exact hardware-level math that makes it possible. Welcome back, listeners, to the Neural Intel podcast. Let's dive into today's topic. As always, we'll focus strictly on the technical details and implications of the technology we discuss.
Exactly. No fluff, just the engineering.
So to stay updated on the latest in AI and ML, visit our blog at neuralintel.org and check us out on YouTube, Apple Podcasts, and Spotify. Before we jump into the deep end, let's lay out the hook, the problem, and the solution for this deep dive.
Let's do it.
The hook is the newly released DeepSeek-V4 technical report. We are analyzing the 1.6 trillion parameter V4 Pro and the 284 billion parameter V4 Flash models.
Massive models.
Massive. And the problem we are addressing is the quadratic computational complexity of vanilla attention. It creates this prohibitive bottleneck for ultra-long contexts, like that 1 million token window, especially during complex reasoning.
Right, because scaling laws essentially hit a physical hardware wall when you literally run out of VRAM and compute.
Exactly. So the solution, which we will spend our time unpacking today, is how DeepSeek-V4 completely overhauls the architecture. They're using hybrid compressed sparse attention, heavily compressed attention, manifold constrained hypercorrections, and the muon optimizer.
It's a massive stack.
Yeah, and it enables massive context scaling with just a fraction of the traditional overhead.
So to really grasp the magnitude of the solution, we have to look at the sheer physics of the problem we've been stuck on for years, right?
Yeah, absolutely, because every time you feed a prompt into a large language model, the network computes a key and a value vector for every single token.
And in a standard transformer architecture, to predict the next word, the current token, the query, has to mathematically attend to the key and value of every single token that came before it.
Which gets out of hand fast.
Insanely fast.
Yeah.
I mean, if you are a CTO trying to build a persistent software engineering agent, and you want that agent to hold a, say, 100,000-line code base in its working memory, you have to store the key and value vectors for all 100,000 tokens in the GPU's ultra-fast high-bandwidth memory.
The VRAM.
Right, the VRAM. This is the KV cache. And it grows linearly with the sequence length, while the compute required to read it grows quadratically.
Wow.
So when you try to push that to 1 million tokens, the KV cache alone demands terabytes of VRAM per sequence. You simply cannot physically fit it on a cluster without the inference costs just destroying your business model.
Which brings us to the scale of what DeepSeek actually built to sidestep this whole thing.
Yeah.
Because the V4 Pro model is, well, it's huge. It's a 1.6 trillion total parameter model.
Right.
But it's utilizing a mixture of experts, or MOE architecture. So for any given token passing through the network, it only actively uses about 49 billion parameters.
Yeah, which keeps the active compute somewhat manageable.
Exactly. And the smaller model, V4 Flash, has 284 billion total parameters, but activates only 13 billion per token. But even with MOE keeping that active compute lean, you still have the KV cache problem.
Oh, absolutely. Storing 1 million tokens of context would still bring the hardware to its knees.
Right, so their first major architectural intervention to solve this is compressed sparse attention, or CSA. I really want to spend some time here, because it is an incredibly specific, mathematically precise operation.
It is. I mean, CSA is where we start seeing the departure from homogeneous attention.
How so?
Well, in standard attention, every token gets its own distinct key and value vector, right? CSA challenges that premise. It basically asks, do we really need a unique high-resolution memory entry for every single preposition and article in a document from, 800,000 tokens ago?
I'm guessing the answer is no.
Right. The answer is a hard no. CSA compresses the KV cache of every M tokens into a single entry. For the V4 architecture, they set M equal to 4.
Okay, so a sliding block of 4 tokens.
Exactly, taking a sliding block of 4 tokens and fusing their representations into one. Instantly, the sequence length of the KV cache is reduced to 25% of its original size.
That's huge.
Wow.
But I am looking at the mechanics of how they actually achieve that fusion, because if you just average the vectors together, you just blur the semantic meaning completely.
Oh, yeah. A simple average would destroy the signal.
Right. So they use a projection method to generate 2 distinct series of KV entries, which they denote as K and Qui, along with a set of compression weights. Then they apply a row-wise softmax over 2 meter elements, which would be 8 elements in this case, to normalize those weights.
And then comes the Hadamard product.
Right, followed by a Hadamard product.
Yeah, and that Hadamard product, which is really just element-wise multiplication, is the critical operation here. They essentially weighting the importance of the features before fusing them.
So they aren't treating every token equally.
Exactly. But the most elegant part of the CSA design is the overlapping index structure. The compression doesn't just happen in rigid, isolated blocks of 4.
Right.
Each compressed entry is derived from 2-meter tokens, so 8 tokens total, but the window actually overlaps with the adjacent blocks.
Okay, kind of like image compression.
Yeah, perfect analogy. Think about compressing an image. If you use rigid blocks, you get artifacting and jagged edges right where the blocks meet. By overlapping the compression windows in the sequence, the model captures a smooth, mathematically blended representation of the local context.
Oh, I see. So the transition from one compressed block to the next is continuous.
Precisely. That prevents the degradation of meaning at the boundaries of the compression blocks.
Okay, so we now have a KV cache that is a quarter of the size and smoothly blended. But the compute required to calculate the attention scores across even a compressed million token sequence is still massive.
Massive.
And this is where they introduce the lightning indexer to handle the sparse attention component, right?
Yeah. And if you are an MLOps engineer, the lightning indexer is basically the component that saves your latency budget.
Because attention is just so heavy.
Right. Calculating attention requires a massive dot product operation between the query matrix and the key matrix. Doing that across hundreds of thousands of compressed tokens is incredibly slow. The lightning indexer acts as a highly optimized filter.
How does it filter?
It uses a low-rank query projection. So for any given query token, it compresses the query vector down into a much smaller latent dimension. It then projects it back up and computes index scores against the compressed KV blocks.
Wait, so it's not doing the full attention math?
No, it does not compute the full attention matrix at all. It just computes a really fast, low-resolution relevance score. Then it uses a top K selector to choose only the most relevant compressed KV entries. The heavy, full-resolution core attention operation is only executed on that tiny subset of selected entries.
It's like skimming the index at the back of a textbook to find the exactly 3 pages you need, rather than reading the entire book word for word every time you have a question.
That is exactly what it is.
And what's wild to me is the precision format they use for this lightning indexer path. They are running the query key projection path in FP4 precision.
4-bit floating point.
The 4-bit floating point.
Yeah.
The math is executing with incredibly low precision, which means the throughput on the tensor cores is absolutely blinding.
Yeah, and it can afford to run in FP4 precisely because it is just an indexer. It doesn't need to capture the nuanced semantic weight of the token. It just needs a rough heuristic of, is this block relevant to my current query?
Right.
The actual value extraction happens later in much higher precision.
Okay, so that covers the compressed sparse attention layer. But DeepSeek interleads CSA with a second mechanism, heavily compressed attention, or HCA.
Yeah, and this is where it gets extreme.
Right, because if CSA is carefully compressing 4 tokens into one with overlapping windows and sparse retrieval, HCA is doing something completely different. It uses a compression factor, denoted as M prime, of 128.
128 tokens consolidated into a single KV entry.
Exactly. That is a massive squeeze.
It is. And HCA abandons the sparse retrieval entirely. It applies dense attention. The query attends to every single entry in the HCA cache.
But doesn't that defeat the purpose of dense attention being slow?
Normally, yes, but because the sequence has been compressed by a factor of 128, dense attention is suddenly mathematically trivial.
Oh, because the sequence is so short now.
Exactly. If you have a sequence of 128,000 tokens, the HCA cache only contains 1,000 entries.
Wow.
Computing dense attention over 1,000 entries takes fractions of a millisecond. In the V4 architecture, they actually alternate these layers.
So they weave them together.
Right. You might have a CSA layer doing fine-grained, top-K sparse retrieval, followed by an HCA layer maintaining a highly compressed global bird's-eye view of the entire document.
Okay, so let's talk about the hardware constraints of projecting all this back to the hidden state. Because in a standard transformer, after you calculate attention across all your multiple heads, you concatenate those head dimensions back together into one massive vector, and you run a linear projection back to the hidden state size.
Yeah, the output projection.
Right. And for a model with 1.6 trillion parameters and massive embedding dimensions, that single matrix multiplication is incredibly expensive.
Oh, it's a huge bottleneck. But they mitigated that using what they call a grouped output projection.
How does that work?
Instead of projecting the entire concatenated massive dimension all at once, they split the attention heads into logical groups. Each group is first projected down to an intermediate, smaller dimension. Only then are those intermediate representations concatenated and projected to the final output.
Ah, so it's a dimensional bottlenecking technique.
Yes. It drastically reduces the total number of floating point operations required for the output projection without sacrificing the expressive power of the multi-head attention mechanism.
Makes sense. We also need to look at how they are storing these vectors in memory, because precision formats clearly play a huge role in their efficiency. They use a mixed storage format for the KV cache.
They do.
We mentioned FP4 for the Lightning indexer, but for the actual cache storage, they use BF16 strictly for the rotary positional embedding dimensions, the ROPE dimensions, and FP8 for the rest of the feature cache.
Right, and the rationale there is driven entirely by the mathematics of positional encoding. ROPE encodes the relative position of tokens by rotating their vector representations in a hyperdimensional space.
Okay.
When you are dealing with a 1 million token context, the angles of rotation become incredibly granular. If you try to store those rotation angles in an 8-bit format, the quantization error literally destroys the model's ability to distinguish between token position 800,000 and token position 800,005.
Because there aren't enough bits to represent the tiny angle difference.
Exactly. Positional accuracy over extreme lengths requires at least 16 bits of precision. But the actual feature dimensions, the parts of the vector that encode the actual meaning of the words, are remarkably robust to quantization.
So they drop those down to FP8.
Yeah, and storing those in FP8 cuts the memory footprint exactly in half compared to pure BF16, with basically zero measurable loss in semantic reasoning.
I love that. But I have a pushback here. If we are compressing every 128 tokens into a single KV entry in the HCA layers, how are we not completely destroying the model's ability to track fine-grained, immediate local context?
That's the exact question you should be asking.
Right, because if I give this model a complex system prompt and the very last sentence I write is a highly specific, nuanced instruction, how does the model not lose the plot entirely?
That is the fundamental vulnerability of high-ratio compression architectures. If you compress everything, you lose the immediate, localized syntactic flow. To counteract this, DeepSeek engineered a supplementary parallel branch within the attention layers called sliding window attention, or SWA.
Ah, sliding window.
Yeah. Alongside generating the highly compressed CSA and HDA entries, every single query token also generates a specific number of completely uncompressed, high-fidelity KV entries. For V4, they set the SWO window size to 128.
So wait, it's operating on two entirely different focal lengths simultaneously.
Exactly. When a token is predicting the next word, it is querying the compressed HCA cache to understand the global context of the entire million-token document. It is querying the CSA cache to pull specific top K relevant facts from the distant past.
Okay.
And simultaneously, it has flawless, uncompressed, token-for-token access to the immediate 128 preceding tokens via the SWA branch.
So the local dependencies, the exact phrasing of your last instruction, the immediate causal structure of the sentence it is currently writing, all of that remains perfectly intact.
Perfectly intact.
Wow. Okay, neural signal check. Here's why this development actually matters at a technical level. By abandoning the traditional concept of homogeneous attention and intentionally splitting the mechanism into three distinct pathways, a Lightning indexer running in FP4, an ultra-compressed long-range memory using HCA, and a flawless short-term memory using SOWAY DeepSeek has reduced single-token inference FLOPs to 27%. And the total KV cache memory footprint to just 10% compared to their previous architecture, DeepSeek-V3.2.
It's unbelievable efficiency.
It is. This is not just a marginal optimization. If you are a CTO designing the orchestration layer for an enterprise AI deployment, this is a fundamental architectural shift that suddenly makes 1 million token agentic workflows financially viable. You can build persistent, long-horizon agents that maintain massive states without burning your entire cloud compute budget just to hold the prompt in memory.
Right, it alters the unit economics of context.
Totally.
The problem, however, is that while you have solved the memory bottleneck at the attention layer, you have introduced a deeply heterogeneous, highly customized mathematical pathway into the network.
And that causes problems.
Massive problems. When you take these interleaved CSA and HCA layers and stack them up 61 layers deep inside a 1.6 trillion parameter mixture of experts model, the training dynamics become violently unstable.
I can imagine.
You create massive gradient routing nightmares. The signal passing through the network during the forward pass will either basically vanish into nothingness or explode to infinity.
Which means we need to look at how they engineer the residual stream to survive this. Let's dig into manifold-constrained hyperconnections, or MHC, and the muon optimizer.
Okay, let's break it down.
So, in a standard transformer, you have residual connections. You take the input of a layer, pass it through the attention mechanism in the feed-forward network, and you add the original input back to the output. This skip connection allows the gradients to flow smoothly backward through the network during training. A few architectures recently introduced hyperconnections, which expand the width of that residual stream by a scaling factor. It decouples the residual width from the hidden state size, giving you more expressivity. But V4 pushed this into entirely new mathematical territory with MHC.
Yeah, because the standard hyperconnection is powerful, It gives the network a wider highway to pass information forward. But when you expand that highway and you pass the signal through a learned linear transformation matrix at every layer across 61 layers, the numerical instability compounds exponentially.
Oh, because of the multiplication.
Exactly. If the largest singular value of that transformation matrix is even slightly greater than say 1.05, and you multiply it by itself 61 times, the signal explodes. The activations hit an end, not a number, and your whole training run collapses.
And at that scale, a collapse is extremely expensive.
Devastatingly expensive. So to solve this mathematically, rather than just using heuristic workarounds like layer normalization, MHC introduces a strict topological constraint. It forces the residual mapping matrix to be projected onto a specific mathematical manifold known as the Birkhoff polytope.
The Birkhoff polytope.
Yes, which is the manifold of doubly stochastic matrices.
Okay, let's visualize that constraint for the listeners. What physically happens to the numbers when a matrix is constrained to the Birkhoff polytope?
Think of it like this. A doubly stochastic matrix is a square matrix where all the entries are non-negative, and the sum of the values in every single row is exactly equal to 1, and the sum of the values in every single column is exactly equal to 1.
Okay.
Think of it like a perfectly balanced closed fluid dynamic system. The total amount of water entering the network of pipes is exactly equal to the total amount of water leaving the network.
So the pressure can be routed differently internally.
Right, but the overall pressure of the system can never increase and it can never decrease. By mathematically constraining the residual transformation matrix to this manifold, you guarantee that its spectral norm is bounded by exactly 1.
Oh, wow.
It is mathematically impossible for the signal to expand or explode as it passes through the residual stream, no matter how deep the transformer stack gets.
It's a structural guarantee of stability. You aren't just hoping the gradients behave, you are confining them to a geometry where they have absolutely no choice but to behave.
Exactly.
But enforcing that geometry dynamically on a matrix that is constantly updating during backpropagation across thousands of GPUs is incredibly difficult. How do they actually compute that projection onto the manifold on the fly?
They implement an iterative algorithm called Sinkhorn-Knopp. It's a beautifully simple but powerful process.
How does it work?
Given the raw weight matrix, you first apply an element-wise exponential function to ensure every single value is strictly positive. Then the algorithm begins alternating normalizations. Yeah, you normalize all the rows so they sum to 1, but doing that disrupts the columns. So you normalize the columns so they sum to 1.
And that messes up the rows again.
Exactly. Doing that slightly disrupts the rows again. You repeat this alternating normalization process. For MHC, DeepSeek found that running exactly 20 iterations of Sinkhorn-Knopp during the forward pass is sufficient to reliably converge the matrix onto the Birkhoff polytope.
20 iterations per pass.
Yes. This dynamic constraint solves the exploding gradient problem structurally at the lowest architectural level.
That is incredible. And alongside that structural fix for the residual stream, they overhauled how the model actually updates its weights. They abandoned the industry-standard AtomW optimizer for the majority of the model.
A huge move.
Yeah, I mean, they retained AtomW for the embedding layer and the final prediction head, but for all the hidden layers, the attention blocks, the MOE experts, they implemented the muon optimizer.
Right, because AtomW is fantastic, but it updates weights independently on a per-coordinate basis based on moving averages of the gradients. Muon, which stands for Momentum Orthogonalized by Newton-Schultz, treats the gradient update as a 2D matrix operation.
Okay, so a holistic update.
Exactly. It fundamentally changes how the momentum matrix is processed by explicitly orthogonalizing it before applying the update to the weights.
And orthogonalization does what exactly?
It ensures that the update steps are maximally efficient, moving the weights in directions that are mathematically independent of each other, which massively speeds up convergence and improves overall training stability.
Makes sense. The technical report actually outlines the exact breakdown of the mathematical iterations used to achieve that orthogonalization. It's a highly specific 10-step process per training step using hybrid Newton-Schultz iterations.
Right.
The first 8 steps utilize a specific set of coefficients designed for rapid convergence, violently driving the singular values of the momentum matrix close to 1. Then the final 2 steps switch to a completely different set of coefficients designed purely to stabilize those singular values precisely at 1.
It's an incredibly targeted mathematical operation running millions of times a second.
Yeah, and it requires immense computational efficiency to execute without becoming a bottleneck. But even with the Sinkhorn-Knopp iterations guaranteeing residual stability and the muon optimizer orthogonalizing the updates, training a 1.6 trillion parameter mixture of experts model is still an inherently chaotic, spiky process.
Extremely chaotic. The routing mechanism itself introduces extreme volatility. They had to implement further targeted fixes, specifically anticipatory routing and SWIGLU clamping.
Let's look at the routing problem.
Yep.
Because in MOE architecture, you have a router network that looks at each token and decides which of the expert networks should process it. This router is learning and updating its parameters at the exact same time the experts are updating their parameters. This creates a synchronous feedback loop. If an expert gets slightly better at a task, the router sends more tokens to it, which causes the expert to produce larger gradients, which updates the router to send even more tokens, until you hit a gradient spike and the training collapses.
Yeah, it's a notoriously difficult self-reinforcing loop to break. Anticipatory routing solves this by deliberately desynchronizing the network updates from the routing mechanism.
You say decouple them.
Exactly. When you are computing the forward pass at training step T, the actual token features and representations are computed using the current up-to-date parameters. However, the routing indices, the decisions of which expert gets which token, are computed using historical network parameters from a previous step, T minus delta T.
Oh, I see. It's like if I'm driving a massive 18-wheeler truck on a sheet of black ice, and I steer based on exactly what the tires are touching at this microscopic millisecond, I am going to overcorrect, enter a feedback loop, and spin the truck out.
Exactly right.
But if I steer based on the trajectory of where the road was a split second ago, I smooth out the microfluctuations and keep the entire system moving forward smoothly. Anticipatory routing breaks the instantaneous feedback loop by introducing a tiny delay in the routing logic.
That perfectly illustrates the decoupling mechanism. It smooths the trajectory of the routing assignment over time.
Love that.
Now, the second fix they applied, SWIGLU clamping, is far less elegant, but empirically it is absolutely necessary.
SWIGLU uses the activation function, right?
Yes, the SWIGLU activation function is the nonlinear heart of the feed-forward networks. DeepSeek explicitly clamps the linear component of the SWIGLU output to a strict range of -10 to +10. Furthermore, they cap the upper bound of the gate component at 10.
Wait, why apply such a brute force hard limit on the math?
Because out in the extreme tails of the distribution, deep inside a trillion parameter network, you occasionally get rogue outlier activations. These aren't meaningful signals, they are mathematical anomalies.
Just noise.
Exactly, dangerous noise. If left unchecked, these outliers propagate through the network and literally blow up the loss. By applying a hard clamp, you ruthlessly truncate these outliers.
Doesn't that hurt the model's intelligence?
You'd think so, but DeepSeek proved empirically that putting a ceiling on the activation function produces zero degradation to the model's final reasoning or knowledge performance. But it entirely eliminates a major source of hardware-level instability.
Wow, it's the ultimate pragmatic engineering move. Sometimes you just have to look at the math and say, nothing useful happens past the number 10, cut it off.
Pretty much.
So now, we have stabilized the training mathematics. The gradients aren't exploding, the routing is smooth, the KV cache is highly compressed. But as any infrastructure engineer will tell you, the moment you solve a software bottleneck, you immediately slam into a physical hardware bottleneck.
Always.
Moving all of these highly customized, non-standard operations across a massive GPU cluster requires low-level metal engineering. Let's look at their custom orchestration, TLAing, and KV disk management.
Yeah, because when you design an architecture this bespoke, relying on standard PyTorch A10 operators is a death sentence for performance.
Why is that?
Well, PyTorch is designed to be general purpose. When you ask it to execute an interleaved array of CSA sparse selections, HCA dense compressed attention, SWA sliding windows, and dynamic 20-iteration synchron knock loops, the CPU-side orchestration overhead becomes catastrophic.
Oh, the CPU can't keep up with scheduling at all.
Right. The CPU spends more time validating the tensors and scheduling the memory than the GPU spends actually doing the math. To circumvent this, DeepSeek manages hundreds of their custom kernels using a domain-specific language they built called Telelang.
Okay, and TLAing allows the engineers to move the host-side logic-like runtime contract checks and tensor layout validation directly into generated host code. By compiling this explicitly, they drop the CPU validation overhead from hundreds of the microseconds down to less than 1 microsecond per invocation.
It essentially removes the CPU from the critical path entirely.
That's incredible. But what I found truly fascinating was their integration of the Z3 SMT solver directly into the kernel compiler. SMT solvers are usually used in formal software verification or advanced cryptography. Why does an AI kernel compiler need formal nonlinear integer analysis?
To understand that, you have to look at the complexity of the tensor index arithmetic they are running. Imagine trying to write the CUDA code for a memory pointer that has to dynamically calculate its position based on overlapping compression windows of m equals 4,
Right.
while alternating with windows of m prime equals 128,
Right.
while managing a rolling buffer of 128 uncompressed SWA tokens.
That sounds horrible to code.
It is. And all while the batch size is changing dynamically depending on how many users are querying the model. The arithmetic to figure out exactly which byte of memory to read or write is mind-bending. If your math is off by a single integer, you read from unallocated memory and you crash the entire cluster.
Which you really want to avoid.
Right. So the Z3 SMT solver translates TLAng's index arithmetic expressions into mathematical theorems. It then formally proves the bounds and safety of those tensor operations before the code is ever compiled.
It mathematically guarantees that memory hazards and out-of-bounds access are impossible.
Exactly.
It's like, if I am managing a factory floor, standard PyTorch is like having a human manager manually check the safety paperwork for every single gear and conveyor belt before we turn the machine on. It's safe, but it brings production to a crawl.
That's a great way to put it.
Using TLAing with the Z3 solver is like having a physicist mathematically prove before the factory is even built that the gears physically cannot collide. Because you have that mathematical proof, you can fire the manager, remove all the safety limiters, and run the factory at absolute maximum speed without fear of a crash.
Yeah, and because of that formal verification, they achieve zero-cost abstraction with exact bitwise reproducibility against handwritten CUDA.
I want to pause on that phrase, bitwise reproducibility. Because for the MLOps teams and researchers managing these systems, this is a holy grail. DeepSeek spent massive engineering resources writing dual kernels, sometimes relying on deterministic atomic operations or specialized sorting algorithms, just so that a token's final output floating point value is identical down to the exact bit, regardless of its position in a bash or how many padding sequences surround it.
It's extreme dedication.
It is. Why go to such extreme lengths to eliminate non-determinism?
Debuggability. At the scale of 1.6 trillion parameters across thousands of GPUs, non-determinism is a nightmare. In standard GPU programming, non-determinism usually stems from the floating point accumulation order.
Because floating point addition isn't associative?
Exactly. Because of how computers represent decimals, A plus B plus C does not always exactly equal C plus B plus A. When you are running atomic additions during a sparse attention backward pass, the order in which the GPU threads complete their math and write to memory is somewhat random.
So you get tiny variations.
Right. This means the final accumulated gradient will have tiny, microscopic variations every time you run the code. In a small model, this doesn't matter. In a 1.6 trillion parameter model, those microscopic variations compound across 61 layers and billions of tokens.
That makes sense.
If you are an MLOps engineer and your loss curve suddenly spikes to infinity on a Tuesday at 3 a.m., you are facing a crisis. Did the model collapse because the fundamental MHC architectural math is flawed? Did the dataset contain a poisoned batch of tokens? Or was it just a random, irreproducible floating point accumulation artifact caused by how the hardware scheduled the threads?
And if your kernels are not bitwise deterministic, you cannot isolate the variable.
You are literally chasing ghosts. Strict determinism ensures that if the math breaks, it breaks exactly the same way every time, which means you can actually isolate the bug and fix it.
Determinism is sanity at scale. Now, shifting from the compute layer to the network layer, let's examine the expert parallelism, or EP, communication bottleneck.
Yeah.
We noted that V4 is a mixture of experts model. This means that as tokens flow through the network, the router decides which expert should process them.
Right.
Since the experts are distributed across thousands of different physical GPUs on different nodes, tokens are constantly being transmitted across the network interconnects. This all-to-all communication is historically the primary bottleneck in MoE scaling. DeepSeek tackled this using a fine-grained, wave-based scheduling system.
Yeah, and to appreciate that, you have to look at the alternative. In a standard EP implementation, the system waits for an entire large batch of tokens to be routed, packages them up, sends them across the network, waits for the specific GPUs to compute the expert layers, packages the results, and sends them back.
So it's blocking.
It is a totally synchronous blocking operation. The GPU compute cores sit completely idle while the network cards transmit data.
Which is just wasted money.
Huge waste. DeepSeek's wave-based scheduling fractures the experts into small, independent waves. As soon as Wave 1 finishes its network transfer, the compute cores immediately begin processing it. Simultaneously, while the compute cores are crunching Wave 1, the network cards are actively transferring Wave 2.
Oh, they overlap it.
They perfectly overlap the network communication entirely underneath the computation.
And they published a highly specific hardware heuristic for this overlap to succeed. They stated that the ratio of compute capacity to network bandwidth must be less than or equal to the ratio of computation volume to communication volume.
The exact math.
Right. For the V4 architecture specifically, they quantified that 1 gigabyte per second of interconnect bandwidth can successfully hide 6.1 teraflops of computational throughput.
It's an incredible metric.
It is. If you are a CTO purchasing hardware, they're explicitly telling you to stop paying astronomical premiums for infinitely scaling network bandwidth. If you design your network topology to hit this specific ratio, the interconnect is no longer the bottleneck. The communication is entirely masked by the compute.
It is a masterclass in software-hardware co-design. You don't build software and hope the hardware supports it. You define the mathematical constraints of the hardware and build the software to perfectly saturate it.
Totally.
They applied this exact same ethos to memory bandwidth with their FP4 quantization-aware training, or QA. To run a 1.6 trillion parameter model in inference, you have to quantize the MoE expert weights to FP4 or 4-bit precision to reduce the VRAM pressure.
Literally.
But DeepSeek engineered a process where the dynamic dequantization from FP4 back to FP8 during the forward pass is mathematically lossless.
Okay, let's unpack that. Because intuitively, going from a low-resolution 4-bit format to a higher-resolution 8-bit format shouldn't recover lost data. If I take a high-res photo, compress it to a blurry JPEG, and then save it as a large bitmap file, the image is still blurry.
Right.
I lost the information during the first compression. How can their upcast from FP4 to FP8 be lossless?
The analogy holds, but you have to look at how floating point numbers are structured. You do, fundamentally, lose precision when you quantize the master FP32 weights down to FT4. During training, they maintain a high-precision master copy of the weights. They simulate the FP4 quantization, but then compute the actual forward and backward passes in FP8.
Okay, so where does the magic happen?
The magic lies in the difference between the specific bit formats. DeepSeek's FP8 utilizes the E4M3 format. That means 1 sign bit, 4 bits for the exponent, and 3 bits for the mantissa, which provides the fractional precision.
Okay.
Their FP4 uses the E2M1 format. 1 sign bit, 2 bits for the exponent, and 1 bit for the mantissa. When they quantize to FP4, they group the weights into tiny subblocks, and each subblock has its own high-precision scaling factor to maintain accuracy.
I'm with you.
When they dequantize from FP4 back to FP8, the E4M3 format has a significantly larger dynamic exponent range, 4 bits versus 2 bits. Because of this expanded exponent capacity, the FP8 container can perfectly absorb both the quantized 4-bit value and the fine-grained scale information of the subblock simultaneously. Wow.
The FP8 tensor perfectly represents the simulated FP4 math without losing a single drop of additional precision during the upcast operation.
So they get to reuse their existing, highly optimized FP8 training pipelines without modification, while perfectly preparing the model weights for blazing fast FT4 inference in production.
Exactly.
Speaking of production inference, Managing the KV cache for a million token sequence using this new hybrid architecture requires a completely novel memory manager.
Oh, absolutely.
You have heavily compressed tokens in the HCA layers, sparsely compressed tokens in the CSA layers, uncompressed sliding window tokens in the SWA layers, and raw tokens still flowing in that haven't hit the compression thresholds yet. Standard key-value memory allocators would fragment and crash.
They'd shatter completely. To manage this, they built a heterogeneous KV cache management system. They split the memory allocation into two entirely separate primary structures based on the life cycle of the tokens.
Okay, what's the first one? First, you have the state cache. This is highly dynamic. It holds the uncompressed SYA tokens and the tail tokens that are too new to be compressed. Because SYA is a sliding window that moves forward with every new token generated, its memory footprint is strictly bounded.
It doesn't grow.
Right. They pre-allocate a fixed-size contiguous pool in VRAM for the state cache, which acts as a highly efficient ring buffer.
Nice. And the second structure?
Second, you have the classical KV cache. This handles the permanent storage for the highly compressed CSA and HCA entries. Because these entries are compressed by factors of 4 and 128, this pool grows incredibly slowly, allowing for massive sequence lengths without fragmentation.
But the real infrastructural challenge arises when you serve agentic workflows. If a user uploads a 100,000 token codebase as a system prompt, and multiple agents are querying it repeatedly, you do not want to recompute the forward path for those 100,000 tokens every single time.
No, that would be incredibly slow.
You want to store that computed KV cache on physical disk, on your NVMe SSDs, and load it into VRAM instantly when needed. DeepSeek outlined 3 specific on-disk KV storage strategies, specifically designed to handle the massive, uncompressed SWA branch.
Because the heavily compressed CSA and HCA caches are tiny, writing them to disk is trivial. The bottleneck is the SWA cache because it stores 128 uncompressed tokens for every single query step across the entire document.
So what are the options?
Option 1 is full SWA caching. You write the entire uncompressed SWA state to disk for the whole prompt. When a query hits, you load it instantly. The trade-off is zero compute redundancy, but it requires a staggering volume of sequential disk writes. It will physically wear out standard enterprise SSDs very quickly.
Got it.
Option 2 is periodic checkpointing. Instead of saving every single step, you only write the SWA state to disk every plea token, say every 1,000 tokens. When a query hits, you load the nearest checkpoint, and the GPU rapidly recomputes the remaining few hundred tokens to catch up.
A nice middle ground.
Yeah, it's a highly tunable trade-off between disk I/O pressure and minor GPU recomputation.
And option 3 is the most aggressive architectural flex. Zero SWA caching. You don't store the massive uncompressed SWA states on disk at all.
None of it.
When a shared prompt is queried, you load only the tiny, highly compressed CSA and HCA caches from the SSD into VRAM. Then, the GPU dynamically recomputes the uncompressed SWA tail strictly on the fly.
And because the SWA window only ever looks back exactly 128 tokens, the computational cost to rederive it from the compressed states is strictly mathematically bounded.
It gives infrastructure engineers a flexible matrix to optimize their clusters. If your cluster is bottlenecked by PCIe bandwidths to the SSDs, you use zero caching and burn a little extra GPU compute. If you have infinite disk speed but no spare GPU cycles, you use full caching. Building a frontier model isn't just about neural network design. It's about building an entire, highly specialized operating system around how tensors flow through silicon.
Absolutely. It's a full-stack endeavor now.
Which perfectly transitions us from the physics of the data center to the actual intelligence of the model. Once this 1.6 trillion parameter foundation model is trained, stabilized, and physically optimized, how do you transform it from a passive next token predictor into an active, sovereign agent capable of executing code and conducting independent research?
Right.
We are now entering the post-training paradigm shift. To build their final agentic models, DeepSeek executed a massive pivot. They completely abandoned the industry standard of mixed reinforcement learning from human feedback, RLHF.
They dropped it completely.
Instead, they adopted on-policy distillation, or OPD.
Yeah, because RLHF was the engine of the previous generation. You have humans grade the model's outputs, train a separate scalar reward model to mimic those human preferences, and then use reinforcement learning to optimize the main model against that scalar score.
But that paradigm breaks down completely when you move to complex reasoning.
Totally. If a model generates a 500-line formal mathematical proof in Lean 4, or writes a deeply complex, multi-threaded C++ backend, human annotators are fundamentally incapable of accurately grading it. We are just terrible judges of superhuman logic.
True.
So OPD sidesteps human grading entirely. Instead of using a scalar reward model, DeepSeek trains over 10 distinct trillion-parameter domain-specific expert models. They have a model trained exclusively to be a master of pure mathematics. They have a model trained exclusively to write complex code. They have a model trained exclusively for logical reasoning.
Okay.
Then they distill the knowledge from all 10 of those massive teacher models into one single, unified student policy model.
The logistics of doing that are mind-bending. The student model generates a trajectory, a sequence of reasoning. During training, the student's policy learns by analyzing its own outputs and trying to align its logic probabilities with the exact probability distributions of the relevant teacher expert for that specific domain. So if it's a coding problem, the student tries to match the coding teacher's internal logic. But from an engineering perspective, how is that even possible?
It's an insane computational problem.
Right, to align probability distributions, you have to compute the full vocabulary logits. The vocabulary size is over 100,000 tokens. If you try to materialize a 100,000 dimension array across the batch size, across the sequence length, for the student and all 10 trillion parameter teacher models simultaneously, that tensor alone would instantly destroy the VRAM of any GPU cluster on Earth.
It would demand terabytes of memory just to hold the probability score.
Exactly. It would just crash.
Materializing the full vocabulary distribution across multiple teachers is physically impossible. This is where their infrastructure team pulled off a brilliant memory trick. During the distillation process, they don't compute the full final logits for the teachers simultaneously.
What do they do?
Instead, they run the forward pass on the teacher models and stop right before the final prediction head. They capture only the last layer hidden states, the dense, highly compressed vector representations, and cache those in a centralized buffer.
Oh, it's smart.
During the actual training step, when the student needs to align with a specific teacher, the system retrieves that teacher's hidden state from the buffer, dynamically loads just that one teacher's prediction head into the GPU VRAM, and reconstructs the full 100K vocabulary logit distribution locally, strictly on the fly.
It's like having a panel of 10 brilliant judges. But instead of all 10 of them talking at the same time and blowing out the audio system, they pass a single microphone back and forth. You only load the heavy prediction head into memory when that specific domain expert needs to speak.
That is a perfect analogy. That is phenomenal infrastructure engineering.
Now, for the generative paths where they still require an active reward signal to optimize against, they introduced generative reward models, or GRMs. And this represents a massive conceptual leap in how we align AI. They dropped the concept of a scalar-based reward model entirely.
Yeah, this is huge.
The main actor network natively functions as its own generative reward model.
Right. Historically, a reward model looks at a piece of code and outputs a single number, say 8.5 out of 10. That scalar number contains very little useful gradient information. Why was it an 8.5? Was it inefficient? Did it have a memory leak?
You just don't know.
You don't know. By forcing the actor network to act as its own GRM, they train the model to evaluate its own generated trajectories using its full internal reasoning capabilities. Instead of outputting a scalar score, the model generates a comprehensive textual critique of its own logic.
Okay, I see.
Because the model's massive internal world model and reasoning engine are fused directly into the evaluative process, the scoring becomes incredibly robust. The model can accurately grade itself on a complex algorithmic task far better than a human-annotated scalar model ever could.
And to facilitate these complex agentic tasks during training and execution, the model needs a sandbox. You can't just have an AI hallucinating code. It needs to compile it, test it, read the error logs, and iterate.
Right, it needs to touch the real world safely.
DeepSeek built a highly optimized execution environment specifically for this called DSEC Sandbox, which stands for DeepSeek Elastic Compute. If you are building AI software engineers, they require a secure, isolated place to run terminal commands and interact with APIs without executing arbitrary remote code on your main servers.
Definitely.
DSEC provides 4 entirely different execution substrates depending on the security and performance needs: function calls, Docker containers, micro VMs via Firecracker, and full-weight VMs via QEMU.
The engineering marvel within DSEC is its layered storage architecture, utilizing EROFS and a distributed file system called 3FS. When an agent requests a complex environment, let's say it needs a full Python backend with PyTorch, CUDA drivers, and a specific database instantiated DSEC does not copy gigabytes of data to spin up that environment.
How does it load so fast then?
The base images are highly compressed, read-only layers mounted directly via the 3FS network file system.
So the data remains centralized, and the virtual machines just stream the specific blocks of data they need on demand.
Exactly. This layered approach eliminates the I/O bottleneck of environment creation. It allows the cluster to achieve millisecond-scale resumption and instantiation of hundreds of thousands of isolated sandboxes concurrently. An agent can spin up a micro VM, compile a C+ script, get the result, and terminate the VM in less time than it takes a human to open a terminal window.
But running hundreds of thousands of sandboxes tied to long-running generative processes exposes you to massive hardware failure rates. If an agent is 800,000 tokens deep into a complex code-base analysis, and the physical GPU computing that specific sequence randomly drops a packet or fails mid-generation, you have a serious problem.
A huge problem.
In traditional training loops, you would just discard that sequence and start over. But DeepSeek realized that if you restart generations upon hardware failure, you introduce a catastrophic length bias into the dataset.
Yes. Length bias is a subtle but destructive force in RLHF and agentic training. If you restart upon failure, shorter responses are statistically much more likely to survive the generation process without encountering a hardware preemption.
Right.
Over millions of iterations, the model implicitly learns that generating short, concise, and often incomplete answers yields a higher reward success rate simply because those answers actually survive to the grading phase. It learns to be lazy.
To surgically remove this bias, DSEC implements a token granular write-ahead log, or WAL. Every single token generated by the model during training is immediately and asynchronously appended to a persistent log on disk.
And this is key.
Yeah, if a hardware node violently fails mid-generation, the system doesn't restart. It spins up a new node, uses the write-ahead log to instantly reconstruct the exact KV cache up to the precise token of failure, and seamlessly resumes generation. No discarding data, no re-rolling the dice, and absolutely zero length bias introduced into the final policy model.
The attention to detail required to identify and solve length bias at the infrastructure level is why these models are performing so efficiently.
Moving from the infrastructure back to the prompt interface, I want to point out the elegance of their quick instruction tokens. In most conversational AI pipelines, when a user submits a prompt, you have a small, secondary routing model that reads the text and decides the intent. It asks, does this require a web search? Does this require code execution? Is this a casual conversation? That routing model adds latency. DeepSeek completely eliminated that secondary layer. They engineered the model to natively inject special tokens like an action or a query tag directly into its own output sequence.
By injecting those tokens into the sequence itself, they reuse the massive high-resolution KV cache that was just computed for the user's prompt. The primary model natively performs its own intent recognition and parallel search query generation entirely on the fly.
That's amazing.
Yeah, it is generating the search query using the exact same deep semantic understanding it is using to formulate the answer. It entirely eliminates the time to first token delay caused by secondary routing APIs.
They also fundamentally changed how they handle the think tags in these agentic workflows. In the previous iteration, DeepSeek-V3.2, when a user sent a new message in a chat interface, the system would flush all the hidden reasoning context, the contents inside the think blocks, from the previous turns to save KV cache space.
Right, it only kept the final textual answers.
In V4, because of the extreme efficiency of the CSA and HCA architecture, they implemented interleaved thinking. The think tags, the model's entire internal monologue and chain of thought, are permanently persisted across user message boundaries.
This is critical for sovereign agents. If you are having a back-and-forth debugging session with an AI over 40 messages, you want the agent to remember the hypotheses it internally discarded 20 messages ago. Interleaved thinking allows the agent to maintain its entire problem-solving state over a massive long-horizon task. It never forgets the logical dead ends it already explored.
Which is exactly the capability you need when you are finally leveraging a fully functional 1 million token context window.
Definitely.
All of these layers, the mathematical stabilization of the residual stream via the Birkhoff polytope, the Z3 compiler verification, the hardware-aware wave scheduling, the shift to on-policy distillation, and the DSEC sandboxing, they all culminate in the final performance benchmarks. Let's look at what this model actually achieves in production scenarios.
Let's do it.
Let's examine reasoning and math first. V4 Pro Max, which is the 1.6 trillion parameter model running with the maximum allotted thinking budget during inference, hits a perfect 120 out of 120 on the Putnam 2025 benchmark.
Wow.
For context, Putnam requires incredibly complex hybrid formal-informal reasoning. It is not just calculating numbers, it is generating proof-level mathematics that requires deep logical leaps. Achieving a perfect score is essentially a flawless execution at the undergraduate math major level.
And we see that same reasoning dominance on the coding side. V4 Pro achieved a Codeforces rating of 3206. Codeforces is the premier competitive programming platform. To put a 3206 rating in perspective, that ranks the AI 23rd among all human candidates globally on the platform.
Just incredible.
It is not just generating boilerplate Python scripts. It is operating at an elite, algorithmic competitive programming level, matching and in some cases exceeding state-of-the-art closed models.
The reasoning is world-class, but what really caught my eye, and what separates V4 from previous iterations, is the knowledge benchmark. Reasoning is one thing, but fact recall is another. V4 Pro Max achieved a massive 20-point absolute jump over existing open-source baselines on the simple QA verified benchmark.
20 points absolute is massive.
A 20-point absolute jump in this specific domain is a generational leap in factual retention. It means the weights themselves are incredibly dense with accurate, recallable information. And when they applied that dense world knowledge to real-world tasks, they set up a fascinating comparison. Agentic search versus traditional RAG.
Array. Retrieval augmented generation has been the enterprise industry standard for 2 years. You use a separate system to search a database, you indiscriminately paste the top 5 text chunks into the AI's prompt, and you ask the model to summarize the text.
Very passive.
Very. It's passive. Agentic search, enabled by those quick instruction tokens and the DeepSeek sandbox, allows the model to actively use search tools. It issues a query, reads the results, evaluates those results in its internal think block, realizes the information is incomplete, refines its understanding, and actively issues new, more targeted queries.
The data.
The data explicitly shows that agentic search drastically outperforms passive RAG on complex, multi-step knowledge retrieval tasks. And surprisingly, because the model is precise about what it searches for rather than blindly processing massive chunks of irrelevant pasted text, the computational cost is highly efficient.
That's great.
There is only a marginal increase in total output tokens compared to the massive input token waste of traditional RAG.
And regarding that 1 million token context window, they validated it using the MRCR benchmark, which is the multiple needle in a haystack test. Instead of just burying one fact in a million words, they bury dozens of discrete facts and ask the model to synthesize them. The stability is incredible.
It holds up.
Oh yeah, retrieval remains near perfect, up to 128,000 tokens. And it remains highly robust all the way up to the full 1 million tokens. It doesn't just passively hold the tokens in memory, it actually comprehends and cross-references them.
The MRCR benchmark is the ultimate proof that the CSA and HCA hybrid attention architecture actually works. They successfully compressed the KV cache down to 10% of its original size without losing the high-resolution semantic fidelity required to find highly specific, uncorrelated facts buried deep within a massive document. The overlapping compression windows preserve the meaning perfectly.
But looking at all this data raises a deeply strategic question. If you are a CTO deciding on your deployment architecture, you have to look at the divergence between the models. V4 Flash, the much smaller 284 billion parameter model, holds its own incredibly well against the massive 1.6 trillion parameter V4 Pro in complex reasoning and math tasks, provided you give it a higher thinking budget.
Right.
If you let Flash generate more internal reasoning tokens, it can solve the logic puzzles. But V4 Flash gets absolutely crushed by V4 Pro in world knowledge benchmarks. What does this empirical divergence tell us about the moat of parameter size moving forward?
It reveals the fundamental physics of neural network weights. You can simulate reasoning and logic through test-time compute. By scaling the thinking tokens in V4 Flash, you give the smaller model the time and the internal scratchpad space to work through complex logic gates step by step and eventually arrive at the correct answer. Reasoning is a process, but you cannot simulate facts. World knowledge requires physical memorization. If the parameter count of the model is too small, the raw data, the dates of historical treaties, the specific atomic weights of obscure isotopes, the syntax of a deprecated programming language, they simply aren't stored in the weights. The capacity isn't there.
So the competitive moat isn't necessarily intelligence or logical capability anymore. The moat is sheer capacity for factual retention. If you want a sovereign model that knows everything without having to constantly spin up external web searches to verify basic facts, you still have to pay the parameter tax. You still have to deploy the 1.6 trillion parameter behemoth.
That is the architectural reality. V4 Flash is like having a brilliant, highly capable intern who can solve any complex puzzle you give them, provided you give them enough time, but they have zero life experience and constantly need access to the internet to check basic facts.
Great analogy.
V4 Pro is the senior professor who has the entire library already memorized. They don't need to search, they just know.
We have covered incredible technical ground today. We started with compressed sparse attention and heavily compressed attention, completely shattering the KV cache memory wall, reducing it to 10%. We unpacked how the Birkhoff polytope and 20 iterations of sinc or NOP mathematically stabilize the residual streams of trillion-parameter networks.
We really went through it all.
We looked at how T-Lang and the Z3 SMT solver provide formal mathematical guarantees for hardware execution, and we explored the paradigm shift of on-policy distillation, replacing traditional RLHF.
Oh.
But I want to leave you with a final concept to mull over, specifically based on the generative reward model data.
Okay.
We discussed how the primary actor network is now natively functioning as its own reward model. It is generating complex trajectories and then using its own fused internal logic to critique and grade those trajectories far better than any separate human-annotated scalar model ever could.
Right.
We are crossing a critical threshold here into true autonomous self-improvement loops. The model is no longer just passively learning from the distilled data we feed it. It is actively learning how to critique its own cognitive processes using its native logic.
It's becoming its own teacher.
Exactly. If the system can generate a complex mathematical proof and then accurately grade that proof as logically sound or structurally flawed without any human intervention or external heuristic, what happens when the student's internal grading rubric mathematically surpasses the teacher's comprehension?
That's the million-dollar question.
When an AI can perfectly verify the absolute truth of a logical concept that a human researcher cannot even mentally map, how do we guide what the network decides to learn next? That is something to think about as you begin deploying these million-token sovereign agents into your own infrastructure.
Something to keep us all up at night.
Definitely. We would love to hear your take on self-critiquing autonomous models in the comments below. Don't forget to visit neuralintel.org for more deep dives into the math and architecture defining the space, and follow us on YouTube, Apple Podcasts, and Spotify. Thanks for joining us on The Bleeding Edge.